Good morning, everyone. So before we start, I want to ask you a quick question. So who here knows somebody who's injured their arm, shoulder, or back? I know I have. So that's pretty much everybody here. So this is one of the things we wanted to address in our project, senior design project this year, and we're happy to present to you Titan Arm.
Good morning. My name is Beattie, and I'm happy to be here today with my fellow design team, Parrotta, Nikolay, Vladimirov, and McGill. 7 months ago, we embarked on this journey to develop a powered upper body exoskeleton for use in applications such as physical therapy. Exoskeletons have been around since the mid-1960s. An exoskeleton is a structural device that attaches to the body's natural limbs and is able to transmit torques and forces in order to complete tasks that can be used in assisted mobility, augmenting strength, or physical therapy. The only caveat to these devices is that they've mostly been used for research purposes and haven't been able to bring out into the general public so that you and I would be able to use this device for something such as physical therapy. So, we were motivated as a team to improve upon this technology and make it accessible for the general population in order to assist mobility. In order to do this, we set some engineering design goals. So, past exoskeletons have often been bulky, invasive, cumbersome, kind of unnatural for the user to wear. So we wanted to transmit the weight from the peripheral limbs and onto an external source, such as a back plate, in order to make a low inertia arm. We also wanted to make the joints non-localized actuation. So instead of having a motor localized at the power joint, we wanted to transfer this onto a back plate or somewhere non-local to the joint. We also wanted this device to be untethered or battery powered. Also battery drivable, have a low-cost development, and in order to determine the success of our device, we measured this against enhancing strength, or the ability to curl a 30-pound weight. And now we have integrated all of these systems together in actuation, structure, and electronics in order to create the Titan Arm. And with that, we'd like to delve deeper into these subsystems, and I'd like to introduce Parrotta, who will be talking about the actuation system.
Thank you, Elizabeth. The actuation system encompasses all of the components that provide power to the suit and also give the user either added strength or resistive force, depending on the application. It's broken into 3 distinct subsystems, being the motor, the cable drive system, and the braking. As a bit of background about cable drives, their purpose is to transmit rotational motion to rotational motion, but in a way that's flexible and can move. This is how we achieve delocalized actuation. This type of system has been used in fields such as robotic manipulation before, but has not been explored within the realm of exoskeletons. With the potential for increased user mobility, we decided to pursue a cable drive system that is both novel and unique to actuate Titan. The first subsystem is the motor. It provides the power for our suit, and it comes from a brushed DC motor from Maxon that supplies up to 10 Newton meters to the elbow. We went with a DC motor because they offer great power-to-weight ratios. They are comparatively inexpensive at the strength requirements that we need, and they're familiar to implement and control. Using a DC motor has enabled us to maintain the mobility, the flexibility, and the independence that our users are looking for. The next subsystem of actuation is the cable drive. This runs from here, this spool, to the matching one on Nico's elbow, and is connected by these cables. The spools were designed and manufactured completely in-house and are attached to twin cables in a pull-pull configuration. This system, we expect it to be heavily loaded, up to 330 pounds of force during operation. So we have sourced custom-made galvanized steel cables to provide a factor of safety of 6.5 with our maximum working load of 40 pounds. By using this cable system, we've been able to provide the desired strength that occupational lifters require, while also ensuring mobility, flexibility, and improving usage. The final subsystem is the braking, and its point is to hold static loads during operation. Our choice of DC motors, while very effective and advantageous for most operation, is actually very bad at holding a static load. This is because if you were to try and just use the motor, it would actually overheat the coils in the motor, causing permanent damage. To prevent this, we've instituted a braking system, which takes that force, relieves the stress on the motor, and makes everything continue working. To achieve that, we have a ratchet and pawl-based system that, on command, will engage and cause unidirectional locking to prevent the arm from falling down. The braking system was an addition to our system that really improved the functionality through its compact size, the simplicity of its use, and the low power to engage and disengage it. And through it, we've been able to create a smaller, more useful, and functional suit for the user. Now, here to describe how all of this actuation system is held together is Nico, who's going to talk about the structure.
Thanks, Nick. So, the structural assembly of the suit is comprised of several parts, whose sole purpose it is to provide rigidity, enable motion, and also to ensure that we are structurally stable enough to support the loads that we are dealing with. Some of the parts that are in this assembly are the backplate that you see at the back, the shoulder linkages here, and also the arm itself. So, we're going to start with the user first, the backplate. Now, the backplate, as you can see, is a very central component to our exoskeleton. Everything is attached to it, both electronics and mechanical components, in a very neat integrated package. But that's not all the backplate is responsible for. Because it is rigidly attached to the user with all of these straps, it is also there to prevent injury, such that when I'm lifting something heavy, my back doesn't give out and I have proper lifting form. Now, moving on to the shoulder components. We wanted to make the shoulder components such that our users would be able to have high mobility while using it. And we also, again, wanted to make sure that it could be structurally sound when withstanding a 40-pound or 30-pound load. So, in order to get mobility, we actually examined the human shoulder joint, which is a ball and socket joint. And in order to get really close to getting that kind of mobility, we instituted a 3-degree of freedom linkage in the shoulder so we can get full range of motion. From there, we explored some of the structural integrity of the suit. We went ahead, we started from simple pencil on paper analysis, trying to work out from the arm all the way up to the shoulder what kind of loads we'll be dealing with, what kind of torque. From there, we moved on to a finite element analysis, as you can see here, to really verify and put this into perspective. This is what drove our manufacturing, and this is what really helped us design this suit further. So all of these methods really helped us achieve something that is very robust mechanically, but it also is very lightweight. So when we were designing all of the joints, we wanted to design something that would be very smooth and very accurate to the user. So as you can see in this explosion view here, in order to do this, we had to have a very complex assembly of bearings and press fits for the user in order to have something that would be non-constrained and wouldn't jam whenever you move it. Now, so for the user, this means smooth motion. but it also smooth motion and reduced force. And for the exoskeleton, it means that you can have a prolonged life because obviously all the component wear is reduced significantly. Now, in order to create all of these components, we went ahead, designed, and manufactured over 38 custom components made out of metal, fabricated here at Penn on numerically controlled CNC machines. We spent over 300 hours machining these components. Now, the accuracy and the precision of the machines that we used enabled us to really have full design freedom of our project. We can create something that would be ergonomic, something that could be sleek and aesthetic, but at the same time, most importantly, something that would meet all of our metrics and all of our design requirements so we can pass them along to the user. Now, to talk a little bit about how this suit is controlled, I'm going to pass it over to our electronics guru, Nick.
Great, thanks, Nico. So we've got a structure and we've got an actuator now. So what do we need? Electronics to tie it all together. The electronics house the brain that pulls up the arm, actuates the brake, and pulls in sensor data from each of the joints. As you can see on the shoulder joint right here, we have a Hall effect sensor in a custom mount. We've got a permanent magnet that's been embedded in this shaft. So as Nico's moving his shoulder around, it's changing the magnetic field and allowing us to get data on the joint angle. This is really useful in applications such as physical therapy, if a doctor would want to monitor a patient remotely, or if the patient themselves wanted to see how they're doing on range of motion increase over a week, 2 weeks, 3 weeks. If Nico turns around, he'll be able to show off the battery system we have. So these are lithium polymer batteries. We chose these for high power output and high power density. So with these batteries, we've been able to achieve over 2 hours of continuous operation, which well achieves our metric of a high use time to charge ratio. The batteries actually charge in less than 30 minutes at a safe charging voltage and current. So if we wanted to go to the next slide, we can show you a little bit about the Hall effect sensors that we mounted. So this is a little clip we took. We're trying to map directly the range of motion of the user, and you can see that in real time we're mapping the joint angle changes. Yep. So if we go down to the next slide, we're going to do a little demo for you. So for our achievements, this is what we've been able to do over the course of the year. So we've got a low inertia arm. As we mentioned before, Nico's got only a spool on the elbow joint, and on the back is the motor. Now this weight is really low. We had a metric of 30 pounds that we wanted to hit. We actually surpassed this pretty far by getting an 18-pound suit, so it's relatively light, as you can see here. In addition, we've got the non-localized joint actuation via the cable drive. We've got untethered, as you see, Nico's not surrounded by any hydraulic cables run into him or anything else. It's back drivable, low cost. We developed this for under $2,000 over the course of the year. And then it also enhances the strength. As you can see, he's going to be doing this for a while to show off that he's not fatiguing as he's lifting this weight. So we were able to achieve these metrics relatively, well, with some time left in the semester. So this is why we were able to implement the braking system, as you can see here. And so Nico can just sit like that for a long period of time, and the motor's inactive. That's really useful for if you want to just hold a static load or doing anything like that. And we also have data streaming, as we showed in the previous slide. Now, by meeting all these metrics, we've produced a proof of concept suit that's applicable in healthcare, occupational lifting, and physical therapy. So all those people you were thinking about before when we started the talk, they could maybe use something like this to help them out.
At this time, we'd like to thank you for your attention. This endeavor would have never been possible without the support of many people, and we're very grateful to them, and also especially Penn Engineering. We would have never been able to accomplish such an amazing project in such a short amount of time without their support. So we really thank you for your attention, and at this time, we'd like to open the floor for questions if you have any.
Love this as part of their recovery process.
Actually, so we did look at a lot of the prior exoskeletons, There's actually a lower body suit called Exobionics that's actually being used for those rehabilitation cases. However, tackling the upper body presented a really nice challenge for us because it's kind of a novel technology. An upper body suit of this nature hasn't really been employed for therapies that we're looking at helping out.
Thank you very much.